to the first potpourri of 2025.
Can everybody hear me?
No.
Oh, how exciting. Okay, welcome to my trip to Egypt and the pre-trip to Jordan. Whatever you like, as long as I can see. Everybody okay? All right. I always knew about Hadrian's Wall, and Sheila tells me it is barely seeable. It's tiny. Let me tell you, Hadrian's Arch is not. It is very, very impressive. And it's in Jerash, which is just north of Amman. That picture is just to prove I was there. Sorry?
When were you there?
Oh, November.
2024?
Yes. Yes.
There's something going on.
I was there. Okay. This is the entrance to Petra, and 90% of the tours to Jordan were canceled because of the wars around them. The guide told us that normally it would take 1 to 3 hours to get through the canyon to get to Petra because of the crowds. We just sashayed in. The people you see here are my group. That's it. There were 15 of us. When we actually got into Petra, there were a few more, but it was certainly not crowded. Obviously, there are good things to be had with wars. I don't know. And this is going along the canyon. I like this. It's kind of a statue without a top. What can I say? And this is Petra. And believe me, it is as spectacular as any picture you've ever seen. You could go to the right and see other buildings and what have you. I sat there for almost an hour on a bench and just absorbed. It was fabulous. And then we went into the desert to see the 7 Pillars of Wisdom. And if that name sounds familiar, it's the title of the autobiography by T.E. Lawrence. And this is where they actually filmed Lawrence of Arabia. How many of you saw that movie? Okay. The carving is of Lawrence, and it doesn't look anything like Peter O'Toole. I know. I thought, really? And then that night we stayed and had a Bedouin dinner. They buried the dinner for 4 hours, and then they dug it up, and it was chicken and lamb and rice, and it was beyond delicious. Then we flew from Amman to Cairo, and here are the pyramids of Giza. I thought I'd be in the desert, and you can see Cairo in the background, kind of almost like downtown Cairo, not quite. Now, one of the guys assured us that the pyramids matched the 3 stars in Orion's belt. I was so excited to share that with you, except it's not true. I know, that was very discouraging. The 3 pyramids weren't planned at the same time. They weren't built at the same time, and they'd have had to match the heavens 4,500 years ago. Poof. And no, our guide assured us they were not built by green aliens. And I keep thinking maybe the aliens just weren't green. However, and they're not a gateway to the stars. I think we all saw that movie. And it's a better match to Orion 10,000 years ago, but then why would you be building pyramids 5,000 years ago? Okay. Suggestion that there were 2 interior shafts in the Great Pyramid, one supposedly pointing to the North Star and one to Orion. But they tried sending a robot in 2020 through those shafts and it got stuck, and they canceled the project. But Egyptians did align the pyramids and temples to the north because they believed that when the pharaoh died, he would become a star in the northern sky. And the corners of the Great Pyramid do align with the cardinal directions north, south, east, west. So that's my astronomy comment about the pyramids. Now, remember the Star of Bethlehem? Remember it led the Magi to Bethlehem. And remember that King Herod was so upset by the birth of a king that he ordered the execution of all male children under the children under the age of 2. The Holy Family, according to the Bible, fled to Egypt, and the Coptic community believes they fled to Cairo, and here is where they landed. The Coptic faith was the major faith in Egypt until Islam arrived. Now, this was the Valley of the Kings, and on the other side is the actual mummy of King Tut. Kind of short, kind of dark. What can I tell you? His sarcophagus is in the old Egyptian museum, not the new one yet, the old one. And we did see several tombs. This one was the tomb of Seti, the father of Ramesses II. The colors were absolutely spectacular. You'd swear they'd just been done. And they've been around a while. Then we flew to Luxor and got on our boat and sailed up the Nile. Now each side is nice and green and lush due to the water of the Nile. There's no more flooding thanks to the Aswan Dam. And farmers on either side can grow sugarcane, bananas, huge cabbages, oranges, and cotton. And then just a little bit beyond that, that's the end of the green and the desert starts. 10% of Egypt is habitable. The rest is desert, and it has a population of over 100 million. We sailed up the Nile to Aswan. We had some stops. I'm not going to show you everything, but I wanted you to see, this is the dam that was built by Nasser to control the Nile. Then we sailed back to Luxor, and trying to think, my left side, that side, is Karnak. It was spectacular, spectacular statues. And then on the other side is the Temple of Luxor. And do you see what I see? In between was Venus. Now, when I saw it, there was only one star. I don't know why my camera picked up 2 stars. I only saw 1. But it was very impressive. And I, of course, turned around and told everybody it was Venus. They were particularly impressed. Now, we're briefly going to talk about Ramesses II. Supposedly, he was the pharaoh who freed the Jews and then chased Moses. And he was the basis for the sonnet by Shelley. How many of you had to learn Ozymandias? Well, thank you, 2 of you. I am Ozymandias, king of kings. Look on my works, ye mighty, and despair. And now nothing remains, and the lone sands stretch far away. But when Shelley wrote that, it was 200 years ago. And since then, they have excavated all kinds of things. And believe me, for a man who reigned for 66 years, he knew how to build statues. There are statues of Ramses everywhere. The little one is from Abu Simbel, and it was moved there because it was going to be drowned when the dam was built at Aswan. The one in the middle is a statue at Memphis. It has an outdoor museum, and this guy was so big, they didn't think he was stable, so he lies down. And the third one is a huge statue at the temple at Luxor. And believe me, there are many, many more. Now, the guide assured me that we would find astronomy stuff. Hey, so this was our last trip actually in Luxor. So I am taking pictures of the ceiling. Now, I could recognize Taurus. Everybody see Taurus? Maybe some of you see Taurus. Good. I recognize Leo. But Hassan was talking about Pisces and about Gemini. And I don't know. Anybody see Pisces? Anybody see Gemini? Anything else? No. Okay. I didn't see it either. But that was the ceiling, and it was really quite spectacular. And then this is the Dendera zodiac. And then that's a picture from the internet. That's another picture. Let's go back to that one. The French saw this zodiac during Napoleon's exhibition. And then an antique dealer was hired to remove it. And he did. with saws, jackhammers, scissors, and gunpowder. And it was moved in 1829 and is in the Louvre. What I saw was a copy. Egypt would like to have it back. Thank you. They'd like the Rosetta Stone back. But hey, and apparently, and I'm not a good enough expert, it says it shows all 5 planets known to ancient Egypt, plus a solar and lunar eclipse. And it apparently matches the sky between June and August of 50 BC. So I will let you look at that. Poof. And then at the same complex, back. You might not recognize this lady because I certainly didn't. It was Cleopatra. And we know because her cartouche says Cleopatra. And she is standing beside her son with Julius Caesar. Now, Octavius, how many of you remember your Roman history? Okay, no hands are going up. Oh, thanks, a little. All right. So Octavius, who was Julius Caesar's nephew and becomes Caesar Augustus, after the defeat of Mark Antony and Cleopatra's suicide, eliminated as best he could all carvings and statues of Cleopatra. He missed this one. And the son, who was the legitimate heir to Julius Caesar, he executed. What can I tell you? Now, from there, from Luxor, we flew back to Cairo and went to the Abdeen Palace. And the Abdeen Palace was the home of the kings of Egypt, the last king being Farouk, who was overthrown by Nasser. It has 550 rooms, beautifully decorated, I might add. And it was built in the 19th century by Ismail Pasha. Now, as a young man, he went to Paris to be educated. And there he fell in love with a charming French woman, but her family opposed the affair. So when he finished his studies, he returned to Egypt and he had 16 wives. But Eugenie was always the love of his life. And it was a star-crossed affair. Notice that? Thank you. Worrying about this. Meanwhile, back in France, Eugenie married a Frenchman by the name of Napoleon III, and she became the Empress of France. Now, in 1869, she was part of the French delegation for the opening of the Suez Canal, and let it be known that she wanted to visit the sites that Ismail had apparently spoken to her. He did not have the Abdeen Palace finished, but he built her 3 small palaces, one a replica of her private apartment in Paris, and he entertained 7,000 to 10,000 people in silk tents along the Nile in unheard of luxury. There is nothing like trying to impress someone. And newspaper reports noted that he seemed so smitten by the Empress that some believed that perhaps they had met before. Mm-hmm. And the next picture is of one of the spectacular chandeliers at the Abdeen. Let every moment be a star moment. And that's it. And how I get out of here, I do not know.
Questions?
Oh, thanks.
Yeah. Wendy, are you going back?
No, I'm going to Tunisia. Yeah. I took a look at Luxor, and I mentioned to our guides that there was going to be an eclipse 6.5 minutes at the end of July. Their face went white and said, that will be unbelievably hot. So I'm going to Tunisia. 5.5 minutes, hopefully not as hot.
Yeah. I was going to ask how hot it was in November.
Jordan was about 20 degrees. So that was very comfortable. Cairo was not bad unless you were actually walking in the sun for any length of time. Luxor was warmer, kind of 27, 28. And again, it wasn't that bad unless you were walking. I was my walking stick, of course. But I can imagine that they assured me that at the end of July, it'll be 40 something.
There in May.
Yeah. And I don't know.
Right.
I think There's about 5 million people there. I don't know where they put the other millions that are all going to show up. Because all those tours are full.
When you showed the zodiac that the Egyptians had said 40 BC, so that's during the Ptolemy times, but did the ancient Egyptians in 2000 and 3000 BC, did they recognize the same zodiac that we like, you know, or from Babylon? Or...
Somewhat, and you're right, it was a Ptolemy. It was done about the time of Cleopatra, either during or after she was Queen of Egypt. I was just stunned that the French came and chopped it down and sent it to the Louvre. And
The British did worse, but we won't go there.
no,
Yeah.
we didn't mention that to our guy
Yeah,
at
yeah.
all.
So, hi, my name is Anagha, and also, as we mentioned before, I just started a youth club with the Samaga chapter. So if you know any youth interested in astronomy and interested in a club for youth in astronomy, so that's 13 to 25, feel free to join and contact me at youthclub.samaga.org. Okay, so hi, my name is Anagha. As hopefully you've been able to hear me for the last little bit, I just started a youth club with the Samaga chapter of RAS. And so if you know any youth who are interested in astronomy and interested in joining a astronomy group, that's between the ages of 13 to 25, feel free to join. We meet at 7 before the last meetings, and also you can contact us at youthclub at mississauga.ras.ca. I believe it's online somewhere. All right. So when staring into the depths of the sky and the universe, I think most people are filled with a sense of awe and existentialism. So many people turn to stories and legends to explain phenomena and patterns, while many others turn to science. So I remember being like 6 or 7 and looking up and wondering, okay, if that's like insanely large, how old is it? Can't be much older than you, right? So today we're going to find that answer together. Table contents. We're going to start with a quick background, make sure we have all of the information we need to actually calculate it. We're going to go into the method and results and our conclusion. So today we're going to find the age of the universe. And when I say we, that is a bit of an exaggeration. So there's 2 main figures who are actually the ones dictating our research and results today. So first, I'd like to introduce you to Edwin Hubble, whose groundbreaking work in the early 20th century revolutionized our understanding of the cosmos. So Hubble's observations of distant galaxies revealed that the universe isn't static, but instead is constantly expanding, which, yeah, perfect, which to us is now common knowledge. So his observation led to the formulation of Hubble's law, which describes the relationship between a galaxy's distance from Earth and its recession velocity, which is the velocity at which an extragalactic object becomes more distant from the Earth. So Hubble's law is on the little moon there. So Hubble's law dictates that the recession velocity is equal to the distance of the object multiplied by a derived constant, which we'll call Hubble's constant. So we're going to get a little technical for a second, but I promise we'll pay off. Essential to Hubble's law is the concept of the Doppler effect, which in cosmology is seen as redshift and blueshift. So the Doppler effect refers to the perception of change in frequency of waves when produced by a moving source with respect to an observer. So have you ever been in a car and heard a police siren? You've probably noticed that the sound changes from like a higher pitch to a lower pitch based on where you're standing. That is an example of the Doppler. In astronomy, if a star or other celestial object is emitting light while rotating and moving away from the Earth, the electromagnetic radiation emitted by the light source would appear to have a downward shifted frequency, which is known as redshift. And when the light emitting object is rotating and moving towards the Earth, there is an upward shift in frequency and a blue shift. So our second key figure is one such celestial object that emits light, and it can be studied to find Hubble's constant. Type Ia supernova, which are powerful supernovae that occur in binary star systems and have a white field. What makes it a key figure is its constant peak luminosity, which makes them valuable when analyzing their light and for measuring cosmic distances. So by comparing their observed brightness, called maximum apparent magnitude of type Ia supernova, with their known luminosity, called maximum absolute magnitude, astronomers can estimate their distance from Earth, which is quite useful. So this method, combined with measurements of the redshifts of those island supernova, enables scientists to map out the expansion history of the universe. And good news, today will help us do it. So let's actually start. So first, we're heading to the Wiseman Interactive Supernova Data Repository, also known as WiseRep. And as you can see, we're setting the object type to type IA supernova. So if you see near object type, I'm a bit prepared to use the laser, I'm sorry. So you can see it's that supernova and IA. And then we click show spectral plot, we can see their spectral graph. And then we choose a type IA supernova and we get to see their spectral plot. So we can select that supernova and then select a point on the spectral graph at random, and we can note down its rest and observed wavelength. I think on this image, you can see that the rest wavelength is 0.0251, and on the graph, you can see like the observed wavelength. So our next stop is the Open Supernova Catalog, which is an online collection of observations and metadata for around 36,000 supernovae. So it's basically Google for like data on individual supernova. So by searching up the name of the supernova, we can find the file containing the data about that specific supernova. And from there, we can find the maximum absolute magnitude and the maximum apparent magnitude values. And now we repeat that 9 more times. To save us all the time, I did that on my own and I wrote them down on a chart somewhere. So let's quickly go back to Edwin Hubble. The formula for the Hubble's constant is recessive velocity over distance. So V over G. So in order to calculate the distance between the Earth and the supernova, we collected the maximum observed magnitude and maximum absolute magnitude of each supernova. So that is on the screen now. And in order to calculate the recessive velocity, we need to calculate the redshift. And in order to calculate the redshift, we collected observed and rest wavelengths from the spectra for different supernovas. So to find the change in wavelength due to the Doppler effect, which is known as redshift, we can use the following formula. So that is like redshift, so Z is equal to the change in wavelength over the rest wavelength. And underneath it, you can see a sample calculation for our first point. So by repeating the calculations for each supernova, we can see the results. Yeah, because Z is less than 1, the recession velocity of the supernova can be calculated through this handy formula, which is V. The recession velocity of the supernova is equal to Z, the redshift, times the speed of light in the vacuum. So you can see the sample calculation for the same supernovas before and all of the data is on the table. So next, to find the distance of each supernova, the following equation can be used. I'm not going to say that equation, so sorry, it's very long. The D is the distance of the supernova, and the lowercase m is the maximum apparent magnitude, whereas the uppercase m is the maximum observed magnitude. And once again, there's the sample calculation, and then next to it is the table with all of the data. So, Hubble's constant. Hubble's constant, as previously stated, is a measure of the expansion rate of the universe, and again, the observation that celestial objects move away from Earth at a recession velocity proportional to their distance. Yeah, so V equals Hubble's constant times D, where V is the recession velocity, D is the distance, and Hubble's constant. You'll find I repeat myself quite a lot. As a result, in order to find the Hubble's constant, the recession velocity can be graphed against the distance, and the slope will give us the constant. Due to the fact that the gradient of the line of best fit would represent Hubble's constant, a point at 0, 0 must be added. So the closer a celestial object is to Earth, the closer its recession velocity will be to 0. So in regards to the universe, I believe the point 0, 0 would represent the Big Bang, but I might have misunderstood that. So, lovely work, everybody. This is our graph. So just quick note, the uncertainties for each data point have been included on the graph, except they're so tiny that you cannot see them. That is good news, I hope. So the line of best fit is y equals 63.261x, and it has an r-squared value of 0.9894. So r-squared values basically indicate how strong like the correlation is of the data. So closer to 1, the higher correlation, and since we're at 0.989, we have a strong correlation. Good news. The slope of the graph is 63.261, which therefore means that Hubble's constant is 63.3, through rounding, kilometers per second per megaparsec. In order to calculate the age of the universe, we can derive a formula based on the equation of motion in Hubble's law. So I'm sure most of us have heard of speed is equal to distance over time. It's basically that simple, except, you just substitute things. So that'll give us the equation the age of the universe is equal to 1 divided by the Hubble's constant. So when our collective value for Hubble's constant is substituted, we get that the age of the universe is 1.55 times 10 to the 10 years. So approximately 15.5 billion years, plus or minus 42.7 million. How I got to that is very, very boring, so I will not be explaining how I got the answer into it. So I did tell you guys one major thing though. We could have saved like past 5 minutes by using this really, really cool, really, really simple tool called Google. So what does Google say? So the scientifically accepted age of the universe is 13.7 billion years. So look, I know 15.5 billion might seem a lot larger than 13.7 billion, but they're like less than 1.8 billion years apart. Come on, what's a billion years to, right? So in comparison to the magnitude of the value, it's not as big of a problem. But you know what? For the sake of science, let's do a percentage error calculation. So percentage error is basically how off we were from the actual value. So as you can see, our collective, the value, the answer we got was only 12.9% inaccurate. So therefore, our result was 87.1% accurate, which I think is great. Good job, everybody. So, sorry. So where did that 12.9% go exactly? So first off, as seen on the distance recession velocity graph, which hopefully I can find, there were 3 like major outliers that didn't correlate with our Hubble's constant. So I think next time using a larger amount of supernova in the research could mitigate any errors caused that way. In addition, due to the data coming from a database, there is a chance of systemic or random errors that took place in the measurement and collection of data. But however, since the majority of data has been collected and verified repeatedly over the course of many years by scientists in the field, this kind of reduces that chance. Third, and least likely, I messed up somewhere. So
Really?
So, also, I don't really know, but thank you. Sorry.
Hello, everyone. My name is Elijah D'Souza. I recently celebrated my 13th birthday, which means I'm in grade 7. I also love sports, and I have a dog named Jupiter, which you can see up there. I've always been looking at the stars, but ever since the solar eclipse, I've been more interested in space and astronomy. And from my spot, the area that I was in for the solar eclipse, the clouds were a bummer, but it was still mind-blowing to me. I've been a RAS member since May last year. Since then, I've volunteered a few times with my telescope, and I was having difficulty with my new telescope, the Celestron 9.25 Evolution. And many people helped me out, so I want to thank the RAS community for that. Visiting the Griffith Observatory. Before visiting the Allan Carswell Observatory, I'd been to the Griffith Observatory in LA, but I never got to see the actual large telescope. The Allan Carswell Observatory telescope has been the largest telescope I've seen. Now, this is my experience at the Allan Carswell Observatory. But before we talk about the telescopes, let's talk about who Dr. Allan Carswell is. He's a physicist. He was a physicist at York University and made a generous donation to the university. Carswell was a co-investigator in the Phoenix Mars mission. He's the founder of Optech, a company that specializes in 3D imaging and space linear solutions. The observatory's first telescope. This is the 60-centimeter telescope, and it's the first telescope at this observatory that I saw. It has 2 large Canon cameras under the telescope for astrophotography. You can probably see it just under. The 1-meter telescope. At the tour that I went to, they showed some of the different objects they have seen through their newest telescope, the Planewave P1000. That's the telescope company and the telescope model. Its mirror is 1 meter long and the mount is Alt-Az, which makes no sound at all. I took a video. The telescope controls. They have a dedicated room that showcases how the telescope operates, checks the weathers, and displays a map of the night sky, indicating the areas accessible to the telescope. Additionally, they showcased a few objects the telescope has captured, like the Moon, Saturn, and M57, the Ring Nebula. I thought this tour was amazing, and I highly recommend going to the observatory on one of their viewing nights, usually on a Wednesday. You can also catch Dr. Hyde's podcast, one of the professors there. Thank you all for listening and being patient, as this is my very first RAS presentation.
And how it just floats, that scope, that now. just-
That's amazing.
Yeah,
How it just moves.
yeah, well, it's actually floating.
Yeah.
Yeah, right.
So Elijah, what do you want to be when you get older?
I do want to be an astronomer one day.
Yeah, when you're 14, what do you want to be?